Dear students, welcome to the online class. I am Dr. S.C. Hiraman. In this video, you are going to study about the Hoff's equation and its limitation. That is, derivation of Hoff's equation. Now, from Hoff's reaction isotherm, from Hoff's reaction isotherm at equilibrium that is delta G naught equal to minus RT ln Kp. Here Kp is the equilibrium constant of a reaction and delta G naught is the standard free energy change. On rearrangement, we get delta G naught divided by T is equal to minus R ln Kp. On partial differentiation, with respect to T, we get dou by dou T of delta G naught divided by T is equal to minus R d ln Kp divided by dt. Suppose this is equation 1 and this is equation 2. From Gibbs-Helmholtz equation, we have delta G equal to delta H minus T delta S. At standard state, that becomes delta G naught equal to delta H naught minus delta T delta S naught. On rearrangement, we get delta G naught divided by T equal to delta H naught divided by T minus delta S naught. Suppose this is equation 3 and this is equation 4. On partial differentiation, with respect to T, we get dou divided by dou T delta T naught G naught divided by T, that is equal to delta H naught. Differentiation of 1 divided by T is equal to, that is T square minus, and differentiation of delta S naught with respect to T, that becomes equal to 0, and this is equation 5. On partial differentiation of this, we get dou by dt delta G naught divided by T, that is equal to delta H naught as it is, and differentiation of T 1 divided by T square minus. From equation 2 and 5, we get R ln Kp, that is d ln Kp divided by dt is equal to delta H naught divided by R, that is T square delta H naught divided by T square. This is equation 6. Equation 6 is known as Van equation. Van equation. Now, Van equation in integrated form. Take equation 6. That is d ln Kp is equal to minus, not minus, that is delta H naught divided by T square into dt, or T square into dt. Suppose this is equation 6. On integration, of equation 6, between the limits that is Kp 1 to Kp2 and temperature T1 to T2, we get integration of d ln Kp is equal to delta H naught into dt divided by R T square, integration from T1 to T2, this is from Kp1 to Kp2, this is equal to ln Kp from Kp1 to Kp2, integration of d ln Kp equal to ln Kp, then delta H naught divided by R, then integration of T square, this is equal to minus T1 T minus T, you may take minus here, and this is ranging from T1 to T2. This is equal to ln Kp2 minus ln Kp1 equal to minus H naught divided by R, into bracket 1 divided by T2 minus 1 divided by T1, that is equal to that is equal to ln Kp2 divided by Kp1 equal to delta H0 divided by R T2 minus T1 T2 minus T1 into T1 T2. Suppose this is equation 7 and this is equation 8, equation 9. It is equation 9 is it is the integrated form of Van Hoff's equation. Van Hoff's equation. Limitation. Limitation. Take integrated equation. That is ln Kp2 divided by Kp1 is equal to delta H0 divided by R T1 T2, then T2 minus T1, T2 minus T1, that is equation 9. In this equation, Kp is variable with T, and we consider H0, delta H0 as constant, but actually delta H not also varies with temperature. It is its limitation. However, H0 may be calculated. H0 may be calculated at different temperatures using Kirchhoff's equation. Kirchhoff's equation, which is delta H naught is equal to delta H naught plus delta alpha T plus delta beta T square plus 1/3 delta gamma T cube, etc. Suppose this is equation 10, where delta H naught 0 is the enthalpy change at t equal to 0, and alpha, beta, gamma, etc. are the heat capacities of the reactants and products.